So, what we've got now is a picture of what we would think of as the Bible of Gaussian process modeling. It's now 8 years old, which I find amazing because I was sort of in the community when it was written, and we were organizing workshops around that time. This book really contains the sort of all the secrets that we all had about how to use Gaussian process modeling up till 2006. And certainly we're not really going beyond 2006 in terms of the modeling side in today's lecture. It's a really good book, and actually the really nice thing about it is it's available freely online in PDF form. So it's the sort of reference for this next bit. So that marginal likelihood, if we go back to, I went the wrong way, gave it all away. Going back to here, this marginal likelihood is a Gaussian distribution. It's a joint Gaussian distribution over y. And implicitly, what I want you to think of is actually there's a Gaussian distribution over f, which has this covariance here, and then a Gaussian distribution over epsilon, the noise, which has this covariance here, and f is being added to the noise to give us y. Yeah? That's our marginal likelihood. So once we've got rid of the parameters, these w's that you've just been playing with and sampling, we have a direct density over y itself that includes a density over f and a density over the noise. So it begs the question, well, what's going on? What does this mean? And really in a Gaussian process, what we do is we consider distributions over functions directly. Instead of thinking, let me have some parameters and that implies this distribution. Now, I don't know, I think there's some interesting, Maurizio and I were just discussing outdoors what the advantage of this approach is, and it was discussed at the last Gaussian process winter school in January. I think there are some significant advantages about interpretability, but we'll develop that as we go along. But what I want to do to sort of see what's going on here is just to consider a Gaussian with a particular structure of covariance matrix, right? And then what I'm going to do is generate a single sample from this 25-dimensional Gaussian distribution. And then I'm going to plot points against their index. So this is a Gaussian with this covariance here. So this covariance is 0. So points that are neighboring are sort of shown along here. The index of the samples is along this axis here, 0 to 25 and 0 to 25. So this is the variance of the 0th point, or it's 0 to 24, and this is the variance of the 24th point, point index 24. Across the diagonal, we're saying that their variance is 1, and as the indexes get further and further apart, we say the variance, the covariance decreases. Now this here is one sample from this covariance, right? From this covariance directly. It's one 25-dimensional sample. And I think it's a remarkably odd thing to be able to do this, to see a sample from a Gaussian density that looks like a very smooth function. I think this is against your intuition about what it would look like. I think the first time you do this is a bit of an eye-opening moment. So I sometimes say that sampling from a Gaussian process is like when you first fall in love with a Gaussian process. Because it's just a really odd thing that you can sample with particular correlation structures and get things that look like functions. Now, what I want to focus on in particular is they've got an important property, Gaussians, that they're closed under marginalization. So what do I mean by that? Well, if we just look at these 2 points here, the index 1 and 2, and I want to ask what's the joint distribution of these 2 points. So probability of, I'm saying this is f1 and f2. So this is giving me the covariance of all points. This is a zero mean Gaussian, so the joint distribution of f1 to 25 is this thing here, and the covariance of these guys here is just taken by taking this box here, right? Focusing on that. Now that's a very odd property of Gaussian distributions. They're closed under marginalization. It's called Kolmogorov consistency, actually. And what it says is that in order to get the Gaussian associated with those 2 points, I can just throw away the covariance rows and columns associated with every other point. I only need to focus on the covariance associated with f1 and f2, and I do the same thing with the mean. So marginalizing in a Gaussian, integrating, high dimensional integral, it's normally very difficult, is trivial. So here we're looking at the covariance of those 2 points, and the colors are probably difficult to see, so we'll just replace them with the actual values. What it says is that the variance of each point a priori is 1, and then the cross covariance between f1 and f2 is 0.96587. Now, because the diagonal is normalized in this case, these are also correlation coefficients. So we've got a normalized diagonal, the diagonal is 1, so this is also the correlation coefficient. So we're saying very strong correlation between f1 and f2. And it's useful to sort of plot what that means in terms of that basis that we talked about earlier. So, as you know, I like to think of these covariances as a basis, and the basis in this case has one vector pointing up here and an orthogonal vector pointing out here. So that one pointing out here is at 45 degrees, and the one pointing out here is again at sort of 45 degrees downwards, but very strongly correlated. So what does this mean in terms of conditioning? So there's 2 operations we can do on a Gaussian where you stay within the Gaussian family. That if I now condition on an observation of f1 and try and predict f2, and that's what I'm claiming is learning, yeah? So I said that earlier, trying to predict y star given y is a conditioning operation. So in machine learning, what we might be interested in doing is taking this as our model, it's our covariance, making an observation of f1, and given that observation of f1, predicting what f2 should be. Now, Gaussians are closed under conditioning as well. You stay within the Gaussian form. And from the perspective of what it means physically, so we talked before about looking at the marginal is like, if I wanted to look at the marginal of f2, it's like looking at this the Gaussian in this direction, and I see that the standard deviation is 1, yeah? Because this curve is a standard deviation of 1. So the marginal of f2 is 1. We also see that here, and the marginal of f1 is 1. To condition, so I think of this as the Gaussian hill, and we're looking at the hill from the f2 direction or f1 direction. To condition, what we need to do is take a slice through the Gaussian hill. So we fix, this is the physical interpretation of what's going on mathematically. If we are convinced that f1 is equal to this value here, which is like minus 0.313, we take a slice through the Gaussian hill at that point, and then we renormalize the hill. So the conditional density of f2 given f1 is minus 0.313 is given by this Gaussian density, which is just the slice through that hill. The slice would not be at this height because it wouldn't be normalized, and then renormalize that to make it a density. Okay? If we were then to multiply P of f2 given f1 by this marginal distribution here, that would give us back the joint distribution, because that marginal distribution would be summing up all the slices, all the different slices through the hills, which would just give us, weighted by a Gaussian itself, which would just give us back this joint distribution. So these are like, this is Bayesian inference in Gaussians. Trivial, yeah? It all stays Gaussian, because the condition is closed under conditional, and it's closed under marginalization. So this is why they can be used as processes, actually. But now we have a prediction of what f2 should be given f1. So f1 is negative, f2 it also thinks is more likely to be negative. So the mode for f2 is not quite at minus 0.313, but it's around about minus 0.3 or something like that. Okay, so this is the sample that we observed. This little x here was actually where f2 was in the joint sample we got before. So it's quite probable, obviously, under the conditional distribution, as you would expect. Now, this is the mathematical form. So if this is the covariance of those 2 values, this is the density of f2 that you can work out. It turns out that f2 is given by a mean which is equal to a weighting of f1 times this term here, the cross term, divided by the diagonal term. So the mean is equal to, so for example, if these terms were both 1, the mean would be equal to 1 over 1 times f1. And the only way that would be possible would be if this was 1, 1, 1, 1. So that would be a degenerate process, actually, and it would have a posterior which was just a sharply peaked line up here. It would have 100% correlation in that direction and no off-diagonal variance. If that were the case, what you would get in this prediction is 1 over 1 times f1, which would say that f2 is equal to f1. And then if you look at what this bit would say, it would say 1 minus 1 over 1. 0. Yeah? So with variance 0. But because we don't have quite 100% correlation, we've got this little 0.96 here. So this says that f1 is 0.96 over 1 of f1. So it's 0.96 of f1. So it's like 0.313 times 0.96. And then this term here is 1 minus 0.96 squared divided by 1. Yeah? So it's, I don't know, about 0.05 or something like that. And that's giving us the form of this distribution here. Mean of about 0.3, just under 0.3, or just over 0.3, and variance of 1 minus 0.96 squared. Okay? Makes sense? So mathematically that's what's happening. And of course, as the correlation reduces, if we look at f1 and f5, and I've now taken the same operation, but I just removed the rows in between, I now have a much looser correlation between f1 and f5. And if I do the same conditioning operation now, I see a much more diffuse prediction. Now, something I'd like to point out is that 0.57 is often thought to be quite a high correlation. So if people are doing statistical tests about whether some disease is being caused by some particular thing, and they're looking for correlation, of course they're very careful about correlation and causality, if they find a correlation of 0.57, people get pretty excited by this high correlation. But it's not that correlated, really, is it? In fact, if you look at the conditional density now, what we see is, of course, this is 0.57 times minus 0.313, the mean. And the mean's not the entire story. So the mean is about minus 0.15. But the variance is 1 minus 0.57. So let's make 0.57 0.5. And so we're getting 1 minus 0.25. So the variance is up 0.75. We need to square root that to get the standard deviation. So 0.8, something like that. So the variance is way up, quite close to our original prior variance. It's not that small at all. And we see that in this standard deviation we're getting here, that things are very diffuse. In fact, we've got probability mass pretty much across the entire location. And then, in fact, if we look at where it ended up, it isn't even in the same half space as f1, despite the correlation. So while they're correlated, it's not saying, you're not saying so much about f5 given f1 than you were before. So we see that in the function, that all the pairs of points that are close to each other, they actually have this same correlation structure because of the way I built this covariance. And any point 5 away from each other also has the same correlation. So look, 5 away, and oh look, you're some distance away. Not necessarily 1, 2, 3, 4, 5. These guys are bang on at the same location. But they could be, you know, if you look, the marginal, what this is saying is that the marginal prediction, if you know that you're here, the marginal prediction of this guy over here is centered, well, for this guy, is centered around about here, this line, but with variance that's quite wide. And then you see that coming out in the structure, that if you move 5 points ahead, you're quite a long way away often from where you started. Yeah? So people get the sense of how that covariance is emerging in the function we see. Now, on interpretability, I think it's a fair point that just if you know the form of this covariance, you don't know what this function is going to look like in terms of this function is actually smooth. It's very smooth. In fact, it's infinitely smooth in terms of if we define smoothness by the number of derivatives of this function that exist, infinite exist. So you can differentiate this function ad infinitum, and you still get an infinitely differentiable function. That's extremely smooth. And that's a bit weird, because it's come out of a Gaussian. And people kind of think of Gaussians as generating non-differentiable functions. Like, if you just sample randomly, you see some sort of noisy thing, yeah? But this is infinitely smooth. You were just sampling earlier from Gaussian processes, polynomials, right? So I guess polynomial functions, their differentiability up to the order of the polynomial. And then it just disappears, yeah? So they have some differentiable qualities. But this one happens to be infinitely differentiable. Okay, now, in general, of course, we want to do this in a multivariate way. So y star is what I said before. That was assuming noise-corrupted test. But if we're just thinking about the function, we've got no noise on it, I'm talking about f star and f. So I think about f as the sample that's coming from the process, the thing I'm defining, and then y is some derived measurement, some corrupted measurement. It may be noise corrupted, or it may be like just a binary observation, or it may be a sum of things. So if we want to talk about f, this fundamental function, we can do it in general in a multivariate way. So the thing we had before was where we had one observation, and we were just weighting that one observation linearly to get our mean. This turns out to also be a linear weighting of our observations. Here's f, and here's f star. The mean is given by if this is the cross covariance between our test points, and this is the covariance of our test points, and this is the covariance of our training points, we need the cross covariance between our test and training multiplied by the inverse of the covariance for the training multiplied by the actual observations. Now, note a couple of things. If f is equal to star, then this k star f is kff, right? So if the test is the same as the training, this is just kff times inverse kff times f, which is f. Yeah? And if that's true on this side, we get kff times kff inverse times kff, which is, so it's kff minus kff inverse kff, which is just kff minus kff. So it's 0. So basically under this model here, it says the training data will always be perfectly recovered. Yeah? Which makes sense. Because we're not saying anything about noise. If everything's correlated in this way, we will recover. If we ask it again about the same points, you will recover the same points. Now, if you add noise in, you can break that. Right, you can, so the way you break that is you add noise in on this side. If you're asking about k of y star is just variance, corrupted variance of the original. And if you're making observations of y, what you get in here is kff plus sigma squared I. And what you get on this side is all this plus sigma squared I. And then you start going outside, you can make noisy measurements. But it's really nice that in the base case, you can see everything working correctly, that if you would recover the training data if you ask about the training data at the same time, unless you start adding noise in. Okay, so that's all about the covariance, and this is the object of most interest. So, yeah, sorry, that's rewriting is that the conditional distribution of f star given f is equal to this mean, this Gaussian here with this mean and this covariance. Okay, so where did this covariance matrix come from? Well, this is the key sort of component of the Gaussian process, is how you define. Okay, just back up a little bit. We haven't said anything about means. We can include means as well. And I'm not going to include means because they're kind of trivial. So if you want to put a mean in, you can do it, and then it just feeds through subtracting off your observations at the relevant points. But they're a distraction because people will generally think that the mean is the interesting bit. And I want you to see that this is a zero mean system. Yeah? A priori it thinks everything's zero mean. But if you sample from it, you get some varying function. So everything's zero mean here, so that we just focus on the covariance because the covariance is where it's at. This covariance that I've shown you above was derived by looking at the squared distances between those indices. So we were indexing from 1 to 25, taking the negative of it, dividing by some scaling factor, and exponentiating. Okay, so this says that if 2 points are close together, relative to the length scale, they'll be strongly correlated. But if they're not close relative to the length scale, if they're a long way apart, they'll eventually, actually this never goes to 0 officially, but numerically it will go to 0 quite quickly. So the distance, the Euclidean distance between these two indices is telling us how correlated these things are in the way we've set things up at the moment. Now, please don't think that this is the only way of defining a covariance function. I'm going to show you later on different ways, but this is a very commonly used covariance function, and it's known as the Gaussian covariance. I don't like the name Gaussian because it's not a Gaussian. It's not normalized. It's known as, I used to like the name radial basis function covariance, and we'll see why it's kind of called that a bit later on. But some people don't like the name radial basis function. You'll see in the code it's called RBF. And so fine, fair enough. So someone called it the squared exponential, and that became quite popular. And I don't like that name squared exponential because it's not actually a squared exponential, because a squared exponential is just an exponential. So I decided to start calling it the exponentiated quadratic, which is what it is. These are of the form of quadratic functions that are exponentiated. People find that a bit of a mouthful, but I call it that to make fun of all those people who told me I couldn't call it the RBF, which is what they just said. So it's the exponentiated quadratic covariance. Now, these little animations here are trying to give you an idea of the sort of functions it generates. So these animations are an idea of Philip Hennig, and I'll try and describe what these animations are showing. They are showing functions sampled from this Gaussian process, which are of constant probability. So Philip does a much better explanation of this than me, but my explanation is you take a sample of the Gaussian process. So these things exist in infinite dimensions, right? Because they're functions. So F is an infinite dimensional space. So we can only ever take a finite instantiation of that. So how do we do these plots? We don't sample infinite things. We build the covariance as you've been doing for some input number of x values. And then we compute the covariance matrix for that. And we sample one sample from a Gaussian with that covariance. Yeah? That's in effect what you've just been doing with the polynomials. But you didn't do it directly. You sampled first a W, and then you sampled then you multiplied by a basis set. Here it's going directly from that marginal likelihood. So to show these plots, which gives you an idea of how these functions sort of wiggle around, we take one sample, and then we take a sample in an orthogonal direction. Well, we find an orthogonal direction, right? And we make sure that those two samples are equiprobable by scaling the second to match the probability of the first. And then, as Philip would talk about it, we take a great circle. We use those things to define a great circle. So on the Earth, a great circle, if we take a point here, and then you take a point in Sheffield, that defines a great circle going around the Earth. And what you're seeing, what you're observing, is, so the Earth is like, if you take the center of the Earth as the mean of a Gaussian, the Earth is a shell of probability in the Gaussian process, if it's spherical Gaussian process, or not quite spherical Gaussian process, yeah? So we're going on a journey, like Magellan, was it Magellan? Or Columbus, for Columbia. We're going on a journey around that circle, trying to get to the East Indies or whatever, but actually we're just going straight through the land, and we're observing the functions associated with those points. And we've done that sort of for 4 different samples simultaneously. So that gives you an idea of what these priors over functions are saying. We'll also try and give you a better idea of what they mean in terms of basis sets. Probably this afternoon that bit's going to be. So how do you build this covariance matrix in general? So you have to think about, so now what you've been doing so far is you've been building basis sets and then multiplying them by parameters. Here you do something different in order to predict with Gaussian processes. So what you always need to answer the question of is what's the correlation between two particular points. So the covariance function is like a machine for giving you the answer to that question. So if I want to know, if I've got 2 points and I've been given the x values for those points, and I'd like you to think about those x's as indices, right? In the first place, I set up the thing by saying we're going to sample a 25-dimensional system with index 0 to 24 or 1 to 25. I used both. And that's the discrete Gaussian setup, right? So I define a Gaussian distribution over a 25-dimensional system, and I can ask about each index. If I wanted, I could do everything I did for discrete Gaussians, and I can ask, what's the prediction of the 24th index given knowledge of the 23rd index, yeah? X now is like a continuous index. So x is giving us so each of these y's, instead of being indexed by something 0 to 24 or 1 to 25, is now being indexed by its input location, which is continuous and infinite. And that's what makes it a process. That you're now able to ask the question about how things correlate across the whole of Columbia if we make X a location in Columbia. So if we want to talk about the distribution of temperatures in Columbia, we could say we've made an observation here at this point X. That's indexed by this point X, and then we make another observation over by the poisonous frog outside the door, and then we take the temperature there, and we expect them to be correlated because they're close. But there's infinite locations I could take between these, and I'm indexing by the location. I'm conditioning on the index. Does that make sense? I think it's a really powerful way of thinking about it. We're going to use that tomorrow when we look at multi-output processes as well. So now, normally, I just look up things when I have the index, right? I go into a matrix and I say, I'm trying to condition between index 0 and index 7. I've stored my covariance matrix. I just go and look that up in the table, which is my covariance matrix. Now we have to look it up in the fount of all wisdom, which is the covariance function. So it's like that table, but only it's a continuous function now. And it can tell us the covariance between any 2 points, here and the frog, or whatever. Here, once we've built that, it can now tell us, when we build a model over here and the frog, it can now tell us the correlation we expect between here and Sheffield. Yeah? Of course, we haven't built probably a very good model to cover Sheffield, but it could in theory do that. So these x's are of that type. And then we ask it to give us each element of the covariance matrix that we need given our input data. So if we're given inputs, or if we're given indices at -3, 1.2, and 1.4, we can just put the first 2 in, which is -3 and -3 go in here. And of course, e to the 0 is just 1, because alpha we've set to 1, because e to the 0 is 1 times alpha. Right? Oh, I keep going the wrong way. However, if we look at x2 and x1, who are some distance apart, and we put them in our covariance matrix generating machine, they're a little bit lower. So we get, of course, it's symmetric because it's distance between the 2 and it's a covariance function. If we do the same for the center, we get 1 again. But we're just feeding these input values along with the parameters into the covariance function. Yeah? So anytime we need to answer a question about a particular location, we call on the covariance function to give us the corresponding element from the covariance matrix. Does that make sense? So here's the color in this case, and it's saying because x1 and x2 are a long way apart, there's very little correlation relative to the correlation between x3 and x2, because they're only 0.2 apart. Yeah? Keep going the wrong way. Oh. So we could do the same thing by adding a new point. So imagine we were given those points and we computed the whole thing there, but now someone says, but I've got an additional measurement for you, and the additional measurement is at x4 is equal to 2. So now I can just compute. And this is what happens at test time. So if you've got the training data like this, you've built your covariance matrix for the training data, you only work with that covariance matrix. But at test time, we now need to ask the question, what is the correlation between our new test point and all our training points? So we need to fill in, of course it's just symmetric, so we need to fill in this row and column. That's what I've been calling K star F in the notation we've used above. And this is what's now used to make a prediction at this new point x4. Okay, and x4 it's a little bit further away from x3 than x2 is. So it's a little bit slightly weaker correlation with x3 and x2 as they are within themselves, but it's a long way away from x1. So it's much more influenced by the values we observe, which we haven't talked about why yet. We haven't talked about the observations, but it's much more influenced by the values we observe at x2 and x4, x2 and x3 than it is by x1. That's what these correlation structures tell us. Okay, so of course we can change the length scale. So I've now increased the length scale, and we're looking at the same initial 3 data points with the larger length scale. Of course, x2 and x3 are still very strongly correlated, even stronger than before. But now if we look at the color map representation of that, we now are saying that there is influence from x1 on x2 and x3. Yeah? So the length scale is allowing these correlations to occur over a further distance. And that will affect what predictions we make. Because an observation of x1 will influence our prediction about x2 and x3 or x4. So to show you what this looks like in practice, Jeremy Oakley is a colleague at Sheffield. Antonio Hagen is one of the originators of Gaussian process modeling, certainly in the modern era. And when I say modern, I mean, I think he published on this in 1978 and has been active in this area ever since. He was also at Sheffield. He's now an emeritus professor, I think. So one of the things they've been interested in is Bayesian analysis of computer code simulations. So earlier we were talking about, imagine you've got some sort of simulation of a factory or something like that. Well, another simulation you could have is that of the climate. So you're doing climate modeling. So the problem with those simulations, as you may know, they take many years of processing time to run. So it's quite expensive for different values of the parameters you choose for the simulation. So this might be, I don't know, how much, some related to how much carbon dioxide we're going to put in the air over the next 10 years. So you test at 2 values. And what you want to know is all the things in between. So Jeremy and Tony have been very active in creating this area where you use Gaussian processes as a proxy for that computer simulator.
So for example, we have a project in which we have like 1,000 ordinary differential equations. The simulator that takes like 12 hours or almost 1 day. There's one simulation.
Yeah, precisely, yeah. So that's a good, So these could be series of ordinary differential equations, partial differential equations, all these physical knowledge going into the system. And to get 1 point out takes 1 day. Actually, that's even pretty fast. When you start getting to climate models, to get 1 point out might take 3 months. So you've got all sorts of questions. Well, how sensitive am I to my input, this carbon dioxide increase and all these sort of things? But you can't now do Bayesian inference or this ABC method we talked about before, because every single simulation of the system takes 3 months. So this is called emulation, and what they do in emulation, or it's one name for it, is they fit a Gaussian process through the original model. Now notice, this is a noise-free setup, like we talked about before. So it's going bang on through the points of the simulation. So these are the observations. Our predictions go right through the observations, which is exactly what they want. In general, they want this because these simulations are deterministic. They're not stochastic simulations like the plants we talked about before. They're actually deterministic systems. So they know that if you ran that model with the same settings again, you would get the same answer. So they want this to have the same answer. And then what they're assuming is some sort of smoothness. Actually, they put all sorts of different things in. I'm oversimplifying it here, but it's an area where Gaussian processes are used a lot, and they want this property that it will exactly interpolate the function. And the covariance I've shown you earlier will always, in theory, exactly interpolate the function. In practice, you can get numerical problems, but in theory, it does exactly interpolate the function. So I'm adding an additional observation. So let's say that we took these 2 measurements and now we're saying, oh, well, we're very uncertain in this region, let's get a new measurement. So I'm adding a different observation. And now once I've got that observation, I can update my predictions about what's going on elsewhere. And now I'm uncertain in those 2 regions, so I get new observations there. Ooh. Now, okay, let's say I don't care about these regions here for some reason. I add the extra observations there. Now this is interesting because actually what's happened is the posterior has collapsed almost to a delta function. Now that's not actually a delta function, but it is massively confident. And what's going on here is the length scale that I've given the model is relatively short compared to the size of observation. So the length scale gives me how quickly it fluctuates. And now the observations are just about the right amount apart that it feels totally confident that posterior is collapsing in the same way we saw it collapse. Well, I showed that these things can collapse under the P of W given F. But notice it only collapses in the region where we've got the data. It doesn't collapse where there's no data. As we move outside, then this is very important in the non-parametric side. As we move outside the region of observed data, it goes large again. Now, another thing that I'll touch on briefly later, I won't do the formalization of it. What does this remind you of? People from signal processing. What does this remind you of? I'm going to say Nyquist. So Nyquist's sample frequencies. What do they involve? So you make an assumption about a band-limited signal. And then you say, if I sample at twice the frequency of my band-limited signal, I will recover the band-limited signal exactly. Okay? And the whole of signal processing is kind of based on that. Now, that assumption turns out to be you're assuming a Gaussian process. But it's a very strong and ugly assumption to make because you're putting zero probability on high frequencies. And this collapse down to a posterior, this proof about, oh, I now will recover the signal exactly, is equivalent to knowing that this thing is actually a delta function. It is not a delta function in this case. There is some small support either side. It's very low probability, but it's some small support. And it turns out, according to Berkner's theorem, that this process we're putting on these points here, it's not a band-limited. So a band-limited signal is assumption of a filter in Fourier space. So where I've used the negative space as well. So this is zero frequency, this is increasing frequencies. Band-limited is this. Massive confidence about a lack of high frequency signals being in place. Whereas this guy here is also a filter in Fourier space, but he's a Gaussian filter. Gaussian filter. He's an exponentiated quadratic filter. There's something we'll touch on a bit later called Berkner's theorem. And in Berkner's theorem it tells us that if we place a filter in Fourier space, then the form of the covariance function will be the inverse Fourier transform of that filter in Fourier space. What's the inverse Fourier transform of a Gaussian?
Gaussian.
It's Gaussian. Only one thing. That sigma in Fourier space becomes 1 over sigma in the other space. So if this filter goes up to be very, very wide, so it assumes all frequencies are present, what does it look like in the other space? Delta function. It's white noise. Yeah? So as you scale this filter up to be consider all frequencies, you start approaching white noise. Exactly as with, you have to do some stuff with the energies. Maurizio and I spent a bit of time arguing about this, and he turned out to be right. That does happen with students quite a lot. So how you scale the covariance function is important, because otherwise you end up with these sort of weird zero energy situations. But what you should be able to be getting from that is that I start talking about signal processing and recreating signals and so on and so forth, Nyquist sampling theorems, you're just putting a Gaussian process prior over a function. And actually it's a pretty dumb one, because it's got super confident assumptions about the frequencies that are there. Now, I don't want to say that people in signal processing are dumb. They're not. Because using that form of filter leads to very efficient algorithms because you know all sorts of things about your signal once you've made that assumption. But of course they've forgotten to separate model and algorithm. And so people in signal processing, I'd say virtually none of them are aware of this interpretation of what they're doing because they're focused only on the algorithm, not the model. But it's informative to go back and say, what is the model by which we are defining this? And the covariance function for that, does anyone know what the covariance of a step is? The covariance function form for
rectangular sync.
Yeah, it's a sync, yeah. So it's a sync covariance function. It's a very odd sort of thing because it actually, and this one indicator of why it's a funny thing, is that the sync, so the covariance function for these signals is a sync, so it's doing that sort of thing. So it's got this really odd characteristic that at a certain distance from here, you're anti-correlated. This gives you a negative value, and then if you move further away, you become correlated again. As a total side effect of a very arbitrary, this frequency is determined by your cutoff frequency, and it's a very arbitrary cutoff, and it has this arbitrary effect on your functions. It's not a good covariance function to use, and also models become degenerate when you start observing things. However, of course, it can lead to algorithms which are very powerful, on which all your mobile phones are operating right now and everything else. It leads to an entire field. But it's worth revisiting the model when you want to do sort of more complicated things like worry about gene expression measurements. So here's the same thing, but now I've added that white noise term in. So we're doing the same type of modeling here, but I've got noise in the measurements now. In both these examples, by the way, these data are sampled from the model. So so everything's matched. This is the odd occasion where you know you've got the ground truth. So these error bars are exact. So in this example, it's no surprise that the data keep falling in the error bars because the data is sampled from the model. And as I increase data, I get improved predictions, but there's some finite level of noise which I'll never get below. Of course, underlying this in the my belief about where this function goes, where f goes, I can become incredibly confident about where f goes, just as I saw before where I had no noise model. But since my observation is f plus some noise, I'll always have a residual sigma squared noise variance in my prediction, just like I do in the regular regression. And here's a fit to that Olympic marathon data. I'd say it's not a great fit. There's all sorts of things wrong with this fit, but it's a particular fit to the Olympic marathon data. It certainly seems to notice that people didn't do much exercise during the sort of Second World War, where things sort of slowed up a bit. So, maybe that feature's there. Its variance is too large because, of course, this is a non-Gaussian noise model, because there's this nasty thing, the point at which, I don't think I'll have to check. I will run one day a marathon as fast as that, but I will never ever run a marathon as fast as any of these things. Yeah. So that is an outlier, and of course the outlier is affecting the noise variance. What you see mostly along here is noise variance. You start seeing variance according to the uncertainty of where f goes as you leave the data here. Okay, so I think in the last 15, I might save that actually. Maybe we'll just go through that in the afternoon. I think what we'll do now is we're going to start the afternoon session at 2:30. Where we'll go through the next part of the lab, which, if memory serves me correct, is effectively starting to look at that polynomial system and turn it into, you can do all the inference we did here. Everything you've done with that polynomial system is directly equivalent to expressing it as a covariance function. The covariance function of that polynomial system is given, well, the covariance matrix is given by this. And we're going to look at what that maps to in terms of covariance function in a bit. But what you're going to do next is, instead of working with phi, this was the form of the marginal likelihood for the thing you've been doing, alpha times this, yeah? So this is the covariance matrix. And what I'm saying now is, in general, we've just got k plus sigma squared if we've got noise. So this bit's equivalent to k. Okay? So what you're going to do now is, instead of working with these guys and W, is you're going to work with this guy. And then you'll do that as the first thing in the afternoon. Now what's the advantage of this guy? Well, as we'll see, this guy solves the question of how many basis functions to have and where to put them. Because this guy can be a non-parametric model. So this guy is involving some multiplyings and addings together, right? Each element of this guy must be derived from some multiplyings and addings of two things that involve x. But if we look at the covariance function we've just defined, you can't see that. It's in there, actually, but it's hidden. And we'll reveal how it's hidden. So you can't factorize that. You wouldn't be able to write down a form that is a factorization of this k. These forms that I like to see k as in factorized into two parts. You wouldn't be able to do that in general for this functional form here. So it turns out that you can't do what you've just been doing in terms of sampling a weight vector and multiplying it by the basis if your covariance is of this type. And that's what makes them so interesting. They're non-parametric models. You can't represent this conditional distribution of f star given f through knowledge of a fixed number of parameters. And that's why I really like Gaussian processes. So you have to do it in this different way, in this way that we've just been showing things, computing the covariance function, conditioning on the various parts. And so you'll do that next, I think, in the lab class this afternoon. And then after that, I'll talk about how to optimize the parameters, or what's going on when you optimize. I won't talk about optimization process. I'll talk about why you can optimize the parameters of these covariance functions and how to see that. And then we'll also look at the relationship between these fixed basis models and these full covariance functions here for a particular case. And then we'll also talk a little bit more about Bochner's theorem and show you some covariance functions that arise from different filters in the Fourier space. Yeah? So we've talked about two. We've talked about a square filter, and we've talked about a Gaussian filter. There's a bunch of other filters you can apply in Fourier space and see what the result of those is. But so when you come back in at 2:30, or bring your laptops, set up, and start continuing to go through the lab where you left off, or start setting up for that, and maybe we'll do what we did earlier. I'll do 20 minutes just going through, showing you what to expect, and telling you which bits to focus on, and then you'll do 45 minutes on your own playing with the parameters of the covariance function. Okay? Good.
I think the transpose was in this one.